As you'll see, calculus is really about developing, as fully and completely as you possibly can, an understanding of how things change. We work with functions which, as you know, provide a link or connection between inputs and outputs. In this video, we explore the way outputs of functions change on average as we vary the inputs. We restrict inputs to some given finite interval of the real line and capture this idea of averaging by finding the slope of the line joining 2 points on the graph of the function. This leads to the notion of the average rate of change of a function. Graphs of functions visualize relationships between quantities represented by variables, say x and y. Here's the graph of some fairly wild fluctuating function y equals f of x. Let's just focus on an interval of inputs x between a and b where a is less than b. There are 2 points on the curve with inputs x equal to a and b, with outputs f of a and f of b respectively. And we can tidy things up by throwing away extraneous points, restricting the domain to the interval from a to b. We like to know or try to gain insight about how one quantity affects or causes changes in another quantity. This is especially important if you want to make predictions. The Reserve Bank wants to know what effect changing the base interest rate might have on certain measures associated with the economy. It could do some kind of mathematical modelling to make reasonable estimates. Almost certainly sophisticated functional relationships will come into play, and the functions could involve many variables. In our case, we simplify things and have just 2 variables, an independent variable x, moving between a and b, and a dependent variable y, whose values are constrained by the graph pictured here. Now, values produced by functions like this one can fluctuate a lot. We can ask, on average, about the overall fluctuation. Here, f of b is bigger than f of a, but how much bigger? Well, the overall change in y values is the difference f of b minus f of a. But we want to interpret this in context. The rate at which this change has occurred is relative to the length of the interval, which is the difference b minus a. The shorter the interval, the faster we think of this change as occurring. The longer the interval, the slower we think of this as occurring. To capture the average rate of change, we should divide the change or difference in the outputs by the change or difference in the inputs. This becomes a formal definition. The average rate of change for y equals f of x over the interval from a to b is f of b minus f of a divided by b minus a. In a moment, you'll realise this is an instance of something familiar. If we join the endpoints, coloured pink in the diagram, by a straight line, coloured blue, then this quotient is just the slope of that blue line segment, the vertical rise divided by the horizontal run. We can think of the line between the endpoints of the curve as smoothing out or ignoring wriggles or fluctuations. So what? How does this relate to reality? Well, road traffic authorities are very interested in the concept of average rate of change. Here's a graph of a function in the xy plane. It describes one of my car trips from Sydney to Melbourne, and the curve emanates from the origin. The vertical axis denotes distance in kilometres from the starting point in Sydney, corresponding to 0, and the horizontal axis denotes time since the journey began. Observe that 873 kilometres is the full length of the journey, finishing in Melbourne. On the horizontal axis, 0 hours, minutes and seconds matches the usual 0. The endpoint of the domain on the x-axis denotes the total time spent on the journey, which happens to be just over 11.5 hours. Notation for counting time in hours, minutes and seconds originated with Babylonian mathematicians who invented the base 60 counting system. Based on dividing units into 60 parts, an hour is 60 minutes and a minute is 60 seconds. At this highlighted part of the journey, where the graph is flat, the car isn't moving and I'm at Holbrook, just over halfway to Melbourne, having a rest. Here's another flat part and I'm at Benalla having an even longer rest. Even though there's a lot of fluctuation, including periods of not moving, we can still ask about the overall average rate of change associated with this journey. We join the endpoints using a straight line and find its slope, which is 873 divided by just over 11.5 hours, which you can calculate to be approximately 75.4 kilometres per hour. This says that over the entire journey, my average speed was about 75 kilometres per hour. Let's zoom in on this part of the graph highlighted here, which looks roughly like a piece of straight line, but with a steeper slope than the average. Here's the highlighted piece enlarged and tidied up a little. The endpoints in fact correspond to speed cameras located at Kulak and North Gundagai. These are average speed cameras, which means that they're used to work out exactly the average rate of change, that is the average speed for that part of the journey. If it turns out to be more than the speed limit, 110 km per hour, then the driver is breaking the law and receives a fine in the mail a few days later. Let's see what happened in my case. I drove fairly smoothly, but not exactly uniformly over that stretch. To get the average rate of change, we join the endpoints and find the slope, which is the vertical rise over the horizontal run, which becomes 16 kilometres divided by 9 minutes and 9 seconds. The denominator converts to a decimal and the fraction evaluates to about 104.9 kilometres per hour. So my average speed for this segment appears to be just under 105 kilometres per hour, safely within the speed limit. But we have to be cautious about accuracy. Notice that though the time has been measured very accurately, and indeed the Babylonians had a reputation for accuracy using their base 60 system, the distance on the y-axis is only quoted to the nearest kilometre. Suppose, for example, that the true distance to the camera at Kulak was slightly less than the whole number on the y-axis, and the true distance to the camera at North Gundagai was slightly more. Then we have to make some adjustments to the previous calculation. And we get an approximation of 110.2 kilometres per hour, which in fact is over the speed limit. You can see how sensitive these calculations can be with regard to possibilities of rounding errors, so one must exercise caution. Estimates of about 110 and 105 agree fairly well to two significant figures, so the mathematics is working, but the outcomes in terms of staying within the speed limit could be drastically different. There are a couple of important issues. The first is the sensitivity of conclusions to rounding errors, which we've just discussed. The second issue is that even if the estimate of 105 kilometres per hour is correct, it's only an average over that leg of the journey, and it's possible to exceed the speed limit at some moment. The graph isn't a straight line. If you were looking at the speedometer of the car, you would notice that my instantaneous speed is in fact fluctuating from moment to moment. It's possible, even though the average was about 105, that the speedometer was reading over 110 at some moment. We want to work towards understanding what we might mean by instantaneous speed. This will be formalised soon using the notion of a derivative, and here's a sneak preview. If you take a line segment with the same slope as the average and move it across the curve, there will be at least one moment in the journey when it becomes a tangent line to the graph. On my journey between Kulak and North Gundagai, you can see this occurred 5 times. At those moments, the speedometer of my car would be showing an instantaneous speed that agreed with the overall average of about 105 kilometres per hour. But if you take a series of snapshots at a cascade of moments, the tangent lines can have varying slopes, sometimes steeper and sometimes shallower than the average. It's the slopes of these tiny miniature tangent lines that become the speeds that are showing instant by instant on the speedometer. If your average speed exceeded 110, then you can be absolutely sure that at some moment your speedometer was showing a speed in excess of 110, which is the basis for receiving a fine. But if the average speed was less, there's no way of knowing for sure that the instantaneous speed was always less than 110. If you're used to glancing at speedometers, either as a driver or as a passenger, then you already have first-hand practical experience with derivatives, and we'll work towards formalising this later in the module. Today we discussed the average rate of change of a function defined on an interval, and saw how to interpret this in terms of the slope of a line joining the endpoints of the curve. This gives us information about how quantities change on average. We looked in detail at an example involving a car trip, interpreting the average rate of change in terms of average speeds over certain legs of the journey. When we start to think about instantaneous speeds or rates of change, such as what you see on the speedometer in a car, then we're well on the way to formalising the notion of a derivative. Please read the notes accompanying this video, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon.